All right, check it out. We are in chapter 5. Exciting. Chapter 5 is another big chapter. We have 9 sections we'll go through in chapter 5, and it's exciting. It's definitely a chapter. Um, it's polynomial functions, and it will come back up in your calculus days. So we're going to give it our full attention. Section 5.1 is called Use Properties of Exponents. Mostly review, but hopefully you're ready for it, and we'll remind you of some of our properties. So the only vocab word that we need to talk about is scientific notation. So scientific notation is a number that is expressed in scientific notation is the form c times x to the power, 10 to the power n. So an example would be, 4 times 10 to the power 6. That's scientific notation. We could also do 2.8 times 10 to the power, -3. Notice that there's always just one decimal place after. You can't, it's not. C has to be a number between 1 and 10, so you couldn't say 28 times 10 to the power -3. It's always two. It's a number less than 10, greater than 1 that goes there, and we'll work on that in a second. So here are all the properties, and again, I'm assuming you've seen this, but I'd love to go through it again. Like it's been a while for you, and you're a little rusty on it, let's say. And so the book's going to use all letters. I'm going to try to give you a few maybe more concrete examples. But here, if I have two of the same base numbers, so it could be an example might be x squared times x to the third, and then the rule says that you add the exponents. Again, you can only do this if you have the same base number. You could even have it like 2 squared times 2 to the third is going to be 2 to the fifth, and this is x to the fifth. So when you have the same base and you're multiplying two of the same base with exponents, you get to add the exponents. That's the rule. Excuse me, got a throat thing. If I have a base number raised to an exponent raised to another exponent, and in the book their notation is a little, to me a little lacking. You'd have like x to the power 2, and then that's raised. Notice I'm going to write this power 3 a little higher. And so this says you multiply the exponents. This is the same as x to the 6th. You multiplied. Really try to keep these two straight. These I think are probably the more important. I mean, they're all important, but if you really keep those two straight, that's a great idea. You can always go to something that's common, right? You can logically think this through. That there are x squared means I have 2 x's, and now I have 3 x's, so my total is 5. Sorry, I can't read that. That's 5. And here, think of having, x squared 3 times. And if I count up all my x's, I have 6 x's. So it should be able to remind that. The power. This rule is kind of distribution. So your exponent gets distributed into both base terms, a to the m, b to the m. Maybe you write this a little bit more as an exponent. It's a little hard to see that. Huge one with negative exponents. So base a raised to a negative exponent, you flip it. Yeah, so x raised to the power -2 is another way of writing, and again, it's just preferential which way you'd rather see it, x squared. So when you have a negative exponent, you flip it. It's not a negative base, all it does is flip. And that's the only operation that the negative does. Anything raised to power 0, anything raised to power 0 is 1. You just got to kind of memorize that one. So anything power 0 is 1. And then you have the quotient property. So a, again, same base, a raised to exponent m divided by a raised to the n. You subtract the exponents. And most of us were pretty good at that, right? So x to the power 5, let's say, divided by x to the power 7. You would subtract these, right? You might think of that now as x to the power -2, which is the same as 1 over x squared. So lots of fun here with exponents. And then this is pretty much similar to this rule, the product property, right? You just distribute this exponent into both bases, even if it's divide. Excellent. So maybe look at a few examples here. So here, this guy, this would be 6 to the power 6 to the power, well, we're going to multiply 2 and 3 and get power 6. 6 to the power 6 comes out to, I have to look at my notes. I mean, you need a calculator, right? This is 46,656. So again, just looking at the rules here. This guy, when I have same base 4, 5 divide the 4 to the 5th divided by 4 to the 3rd, this would be, maybe I should write this is 5 minus 3. And that would give you 4 squared, which is, I could do that one, 16 without the calc. Here, what's going on here? You can actually plug this into your calculator straight up, and I can show you how. You would use the 7 raised to the, so you use that Sargent key and then -4, and it would give you the answer. The book would like you to think at least that this is the same as 7 raised to the power 4. And in your calculator, that would be 1/2401. And if you kept going, it would give you scientific notation of 10 to the power -4. And your calculator doesn't actually work scientific notation this way. It typically would do 4.16 e to the -04. And we can try to talk about that in class, how your calculator works with scientific. Here's an example of scientific notation. So Iceland covers about 1.03 times 10 to the 5th power square kilometers. Nice. Iceland is an island up in the North Atlantic. Beautiful island. Has approximately 2.94 times 10 to the 5th people. Kind of weird way to say the population, but how many people are there per square kilometer? So the solution is basically you take the population of people, divide by the land, right? People per square kilometer. And what's pretty neat here is that you get to cancel these guys. They're the same. You're multiplying, so you're allowed to cancel. Or probably better to say 5 minus 5 is 0. You're left with the 2.94 divided by 1.03. In your calculator, you'd get this answer. And then, the book's kind of nice. Instead of just saying 2.85, they say there are about 3 people per square kilometer. That's not a lot. Nice place to live. So now we're going to get into this game where, we have to simplify expressions. And you've got choices to make. You can see, first of all, you've got the same base x, base y. You have to deal with these parentheses first. So I think the first step and the only step is to distribute this exponent to both the x and the y term. And so this would be x to the power multiply 5 and 3 and 15. So you'd get x to the power 15 over, or excuse me, times y to the power 6. So that's the first step to get rid of the parentheses. We could skip this step here. I don't think we need to write anything here. Now what we're looking at is, hey, what is x to the power 15 divided by x to the power 15? 15 minus 15 is 0, and this really cancels out. So then you're left with y to the power -2. We are going to always present our answers with positive exponents, right? And that's how it goes for this year for us. When you're in calculus, either answer is acceptable, but for us, we need all our final answers to have positive exponents. So that's your final answer. Here we go, another problem. So we've got, again, you kind of have choices here. You could deal with what's in the parentheses first, especially this negative. I'm going to distribute the exponent 2 into both the a and the b term. So this would be a to the power -8 over b to the power 4. And then again, I cannot leave my final answer with a negative exponent, so I will drop the a term to the denominator. Notice I have to write a 1 there, right? And this would be a to the power 8, b to the power 4. And you might do it like a check in the end and say, look, do I have any negative exponents left? Is there just one variable a for the base, one b term for the other base, and then you're pretty much done. Guided practice. So here are 4 problems. Once you hit pause, see if you can clean them up, and I'll show you the answers as soon as you hit play. And there are your answers. So first guy here, you could have distributed the -1 in. You could have as well just subtracted the exponents, right? You have the same base a. So for me, I probably would have done 8 to the power 3 and then still raise it to the power -1. I would have then thought of that as 8 to the power 8/3, and then I would have had to go to my calculator. And example 2 here, the way we look at this, we would say, hey, this is 2 times 7, excuse me, 4 times 7, it's problem 2. That would be 28 times 10, and then these guys, I would add the exponents, and I get 10 to the power 1. So the problem with leaving your answer like this is that your decimal place is here, and you need to move it 1 over. So when we move it 1 over, we add 1 exponent. Does that make sense? So you could have written your answer as 2.8 times 10 to the power 2, or you could just say it's 280. This problem, I think your only first step is to distribute the 7, which gets you x to the 14 and y to the 42, but the negative, you're going to have to drop your answer. So again, if you left your negative in your final answer, you can't do that. That's just the rule. So you gotta flip whatever term has that negative exponent. Be careful here. This negative is not a negative exponent; it's just a negative. So you need to think of this first one as really you're looking at 3 pieces. You've got the digit 2, you've got the base a and a base b. So for me, I think before I distribute the power 3, I would clean up the a term and the b term. I mean, the b terms just cancel. So before you distribute and deal with all that distribution, you may as well just cancel this. This to me becomes -2 a to the power 3, raised to the power 3. So just cleaning up inside the parentheses kind of simplifies now this distribution. I would think of this as -2 to the power 3. So -2 times -2 times -2 is going to be a negative answer. 2 to the 3rd is 8, and then a to the power 3 raised to the power 3 is a to the power 9. Nice job. So here we have kind of a word problem. It's kind of fun. The radius of a beach ball is about 5.6 times greater than the radius of a basketball. How many times as great as the basketball's volume is the beach ball's volume? So let's just walk through the solution here. So the volume of a sphere, nice that they give that to us, right? I don't expect you to have that memorized. So we let R represent the radius of the basketball. And we would say, look, if the volume of the beach ball, right, we would substitute in 5.6 times the radius of the basketball. And then basically we start looking to cancel things. So, quite a bit cancels the volume. But realize that this 5.6 is raised to the power 3. So that's really why this example is here, right? We're going to distribute this power 3 to both the 5.6 and to the radius. And then we see that the radius ends up, the volume, even though the radius is 5.6 times larger, the volume is 176 times as much as the basketball's volume. I think that finishes it. Hey, I'll see you tomorrow in class.